Chapter 8 deals with two different but sort of related problems. There's the minimal surface equation and the time-dependent membrane problem, or string problem, the 1D version. We're only going to look at the minimal surface equation. And the minimal surface problem is to minimize the surface area of a membrane, an elastic membrane that's stretched over some kind of a frame will try to minimize the total surface area. The amount of energy is proportional to the surface area. So we want to minimize the surface area of a membrane whose height is u of x and y. So this is a two-dimensional problem only, with u given on the boundary of some region. And in Calculus 3, we know what the surface area is. That's a standard Calculus 3 problem, that the surface area is the integral over the region, the xy region, of the square root of 1 plus ux squared plus uy squared. If the surface is flat, ux and uy are 0, then the surface area is just the area of the base, and it's always going to be the area of the surface of the roof is always going to be at least as much as the area of the base, and it'll be equal to it if it's a flat, and the steeper it is, the more the surface area will be. Well, anyway, this is the standard Calculus 3 surface area. So we want to find the function u that minimizes this surface area with the restriction that u is known on the boundary. Well, this is very much like the way we derive the beam and plate problems in Chapter 2. We're going to say, well, if you take any smooth function e, which is 0 on the boundary, then u plus alpha e for any scalar alpha will still have the same boundary conditions as u, and therefore its surface area has to be more than or equal to the surface area of u, because by definition u is the one that minimizes that. So if so the surface area of u plus alpha times e, where e is an arbitrary function that's 0 on the boundary, is going to be square root of integral of the square root of 1 plus ux squared plus alpha ex squared, ux plus alpha ex squared plus uy plus alpha ey squared. In other words, just plug in u plus alpha e into here and here, and that's the surface area of this function, which has to be at least as much as the surface area of u, which means that this, as a function of alpha, must have a minimum at alpha equals 0, because alpha equals 0 gives you a minimal surface. Therefore, f prime at 0 must be 0, so just like in Chapter 2. So we take the derivative of this function as a function of alpha for u and e being fixed functions, take the derivative with respect to alpha, and that's just chain rule here, 1/2 times all this to the minus 1/2 times the derivative of what's inside, and that would be 2 ux plus alpha ex times the derivative of that with respect to alpha, which is ex, plus 2 times uy plus alpha ey times derivative of that with respect to alpha, which is ey. So we get this, and at alpha equals 0, that term disappears, and we just have the ux ex plus uy ey over this square root. Well, that alpha is 0, so that'll just be 1 plus ux squared plus uy squared. So we get the dot product of the gradient of e and the gradient of u divided by that, and that has to be 0. So just like in Chapter 2, we do integration by parts. Well, in Chapter 2 we had to do 2 integration by parts, but here only 1, and multidimensional integration by parts. Hopefully you've learned those by now in Appendix A. And basically the divergence of e times this big thing here. So think of this as a product of the function e times gradient of u over that. And the divergence of e times that vector v is going to be equal to e times the divergence of v plus the gradient of e times v. That's basically this version of the multidimensional product rule, except we're starting with this and saying the gradient of e dotted with the vector v, which is the gradient of u over the square root of 1 plus ux squared plus uy squared is equal to the divergence of e times that vector minus e times the gradient of v, the divergence of v. Well, in any case, the formula I just showed you, this would be the u, and this whole thing here would be the vector v. So divergence of e times the vector v is equal to e times the divergence of v plus the gradient of e dotted with v. And then we apply the divergence theorem to this, because we have the divergence of some vector here integrated over the whole region, and that's equal to the integral over the boundary of the region of that vector dotted with the unit normal. And now here we use the fact that e is 0. Remember, e is 0 on the boundary, and so this term disappears, and this all has to be 0 because it's the derivative of alpha with respect to alpha at alpha equals 0. So this integrand has to be 0 because e is an arbitrary function in the interior. So if this is 0 for any e, then the other integrand must be 0 everywhere. And so that's our minimal surface equation. This times e is integral of this times e is 0 for all e, where e is arbitrary, at least in the interior of the region, so this integrand must be 0. So there's a minimal surface equation. And notice it's in divergence form, which means Galerkin method actually has an advantage over collocation. To use the collocation method, and we're going to do both, you have to actually take these derivatives out. So you have to do a little bit of work, not too much, but you have to simplify this to use the collocation method. Okay, so we're going to use both Galerkin and collocation methods to solve the minimal surface problem in a region that looks like this. The upper boundary is y equals to 1 plus x squared. The lower boundary is y equals minus 1 plus x squared. I'm sorry, the upper boundary is 1 plus x squared. Lower boundary is minus the quantity 1 plus x squared. So it's a parabola here above and below, and these are straight lines. So, and on the boundary, u is equal to x squared over 2 around the entire boundary. Okay, well this, for the collocation method, this parameterizes pretty easily, as we'll see, and that's useful for the Galerkin method also. Okay, so we'll solve this problem first using the Galerkin method, which means we have to use the interactive driver. Two-dimensional, I want to use Galerkin this time, collocation next time, double precision. Parameters, we don't really have any. Now this is a simple region we can parameterize. We can let just x be p, and then y would be q times 1 plus p squared. Well, I can look at that more detailed in a minute, but anyway, I'm going to use option 2 and let PD2D generate the initial triangulation automatically, save a little work. It's not that hard to do by hand, but it's easier to do. So I can just let x be p, and then what's y going to be? It could be q times 1 plus p squared, because, and so p will go from minus 1 to 1, because that's the limits on x. And for each x, y goes from minus 1 plus x squared to plus 1 plus x squared. So the limits on p and q are both minus 1 to 1. Got that? X goes from minus 1 to 1. For each x, this would be 1 plus x squared. Y goes from q goes from minus 1 to 1. That makes y go from minus the quantity 1 plus x squared, that's the lower parabola, to plus 1 plus x squared, that's the upper parabola. So that parameterizes easily. And it doesn't matter too much what we take here. So P goes from -1 to 1. So does Q for this region. And we have fixed boundary on all four everywhere. The U is equal to x squared over 2 on the entire boundary. So we need negative arc numbers for each of the 4 arcs. It's actually not going to let us use the same arc number, so we have to give 4 different arc numbers, -1, -2. They have to be negative because fixed boundary. Final triangulation, let's use 1,000. This is if you want a non-uniform triangulation. We haven't done an example like that. It's a steady state problem. Is it linear? No, it's very nonlinear. It involves derivatives of u in the denominator under square root, so it's very highly nonlinear. How many steps? Let's use the of Newton's method. Let's use the default 15. And one equation, let's call the unknown u. Is it symmetric? It actually is, but let's say no anyway. Don't want to bother showing you why. This says strongly advised, yes, so say yes. And now I want to calculate an integral of u because I want to compare the integral of the solution over the entire region with what I get with collocation method. Should get the same answer. No boundary integrals, no direct delta functions. Now, so this is the derivative with respect to x of ux over the square root of blah, 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 plus derivative with respect to y of uy over the square root. So alpha is 0, the right-hand side is 0, and a is going to be ux divided by the square root of 1 plus ux squared. Remember in Fortran, the exponentiation is a double star, not a caret. And b is uy divided by the square root. Now, initial conditions, since this is a highly nonlinear problem, the initial conditions might be important. And since u is equal to x squared over 2 on the entire region, then x squared over 2 seems like a reasonable, why not set u equal to x squared over 2 in the entire region, and that will be correct on the boundary and seems like a reasonable initial approximation. So let's try that. Fixed boundary, yes, we've got 4 of them, -1, and we can't default them because they aren't 0. So it's x squared over 2 on all 4 parts. So I'll have to input all 4 of them here because it wouldn't let me give them all the same negative arc number. Whoops. The solution on the boundary can be functions of x and y. One more. That's it. No free boundary conditions, all fixed. Oh, to 20 by 20 output grid. Now I want to do let's do a surface and a contour plot of the solution. Surface plot of u. And a contour plot of u. That's it. Now run it. And that's the correct integral, so looks like everything's fine. Let's look at the plots. There's the initial triangulation that was all done automatically. Remember, we let P be X, and we did 11 grid lines in the P direction and 11 in the Q direction. Bottom is Q equals -1, the top is Q equals 1. There's the final triangulation of 1,000 triangles. There's a surface plot. It looks like I should have taken more than 20 output points. Since the boundary's not straight, it doesn't look too good here. And the contour plot. Well, there it is. Not real pretty, but get the idea. Okay, so the integral of u was 1.805. Now let's try the collocation method. We could use the GUI, but I'm going to use the interactive driver anyway. So same problem, collocation method. Two-dimensional, this time collocation, double precision. Don't have any parameters. And I'm going to define the region using basically the same equations that we used with the Galerkin method to get the initial triangulation, except we, instead of calling them P and Q, we call them P1 and P2. So I'm just going to let X be P1 and Y will be P2 times 1 plus P1 squared. And again, P1 goes from -1 to 1 because that's the limits on X. Y goes from, P2 goes from -1 to 1 also because Y goes from -1 plus X squared to +1 plus X squared. And let's do 11 grid points in each direction. -1 to 1 are the limits on the constant limits on the parameters P1 and P2. Steady state, not linear. Do 15 steps. One equation, let's call the unknown u again. Let's integrate u, see if we get the same answer. Now the differential equation, it's not divergence form for collocation method. You have to take that divergence out, and that takes a little bit of work, but if you simplify it, it comes out to be uxx plus uyy plus uy squared times uxx plus ux squared times uyy minus 2 times ux times uy times uxy. So that's what you get when you take the divergence and simplify things. So you do have to do some work to get it into a form that collocation can use. Initial conditions, well, let's try x squared over 2 again. No periodic boundary conditions. Okay, on all 4 boundaries, the u is equal to x squared divided by 2. So I have to put u minus x squared over 2 is equal to 0. See, g is what's 0. It's a little different than the fixed boundary conditions for Galerkin is u equals something, gb, but this is just something equals 0. So that's something that's equal to 0 is u minus x squared over 2 on all 4 boundary arcs. See, P1 equals -1 and 1, that would be the left and right. P2 equals -1 and 1, that's the lower and the bottom and top boundaries. Now PD2D will allow you to do a contour plot that reflects the geometry of the region, so let's do that. And that's all. Now let's see if it converges. Looks like it is. 1.806, that's pretty good. Now this is the grid. That means that in each of these squares, the collocation method doesn't use triangular elements. It uses rectangular elements, and each of these, the solution is a cubic polynomial. And there's the contour plot of our solution. I presume it looks like the Galerkin contour plot, since it gave the same integral. We got lucky. Both of these we were able to come up with initial conditions that were good enough to make the highly nonlinear problem converge. But what if we didn't get it to converge? Well, let me show you a little trick that can be used even if it's highly nonlinear and you don't have any idea of what to use for initial conditions. So the trick is to parameterize this, and I'm going to put a beta here times all of that, where beta is going to be defined as okay, and what's going on here? Well, t is it's time for a time-dependent problem, but for a steady state, it's the iteration counter. So the first iteration of Newton's method, t will be 1, and so this will be 0, and beta will be 0, and you see we're just solving Laplace's equation. This whole nonlinear term disappears completely, and you're just solving Laplace's equation. Then the next iteration, t will be 1/5, and then next iteration 2/5, until the sixth iteration it'll be 1, and after that it'll be 1. So basically beta is designed to start out at 0 and gradually increase to 1 and then stay at 1. And so we're kind of leading the horse with a carrot. We're starting out, so it doesn't matter now what initial conditions we use, because the first step will be linear. You're just solving Laplace's equation, so it doesn't matter what your initial conditions are. In fact, let's, just for kicks, let's set the initial conditions equal to something ridiculous. And it should still converge. Minus 1,000, so it should still work. Doesn't matter what the initial conditions are, because the first step it's linear, and you get the exact solution to Laplace's equation, and then after that it becomes gradually more nonlinear until from the sixth iteration on it'll be the full equation. Now I also want to do something else. I want to get some MATLAB plots here, and I'll show you why. So let's remove those C explanation marks from the end so that we can get some automatically get the MATLAB plots. Okay, let's try running it again. Remember, we're starting from initial conditions of u equals minus 1,000 everywhere. Still converges, and this time we have created a MATLAB program, pd2d.m, that I want to run and see what kind of graphics it gives us. And there's the MATLAB plot Surface plot, well, that's gradient of the U. We're not particularly interested in that. This is one we're interested in, and this is for the collocation method in 2D. PD2D will make a contour plot of the solution with the correct geometry of the region, but the surface plot will just be versus P1 and P2, so it'll be over a rectangle. But with the MATLAB plots, you can get the nice surface plot here of with the actual geometry.